All right, this is chapter 12. Now, this is a picture of bent train tracks. All right. And the reason behind this is what happened was when they laid the train tracks down, all right, and then they welded all the tracks together, it then heated up. And what happens when something heats up? It expands. So it linearly expanded and it ended up pushing this all out of whack. Crazy. All right, linear expansion. A steel railroad track that is 40 meters long is attached to a railroad tie while the temperature outside is 10 degrees Celsius. On a hot summer day, the temperature raises to 34 degrees centigrade. How much does the track expand? If the second track is laid end to end with a 4 centimeters between them and they both expand, will the track be in danger of pushing each other away? Now, if you've ever gone over a bridge, a metal bridge, there's little fingers this way and there's little fingers this way that interlock. And in the summer, all right, they're jammed together. And in the winter, they're spread out like this. And those are expansion joints, okay? Concrete in your driveway, all right, a lot of times they will lay it and then they cut expansion joints in it. So when it heats up and it cools down, if it's going to crack, it's only going to crack in those expansion joints. And then sometimes they even put rubber between the expansion joints so that it pushes on it, okay? Now, in this formula, linear expansion, delta L is the change in the length of whatever we're looking at. LO is the actual original, so that's one term. LO is the original length. Alpha is the coefficient of linear expansion, which is in your textbook in chapter 12. And then delta T is the change in temperature, okay? So in this case scenario, we have a 40-meter setup track. This is 12 times 10 to the minus 6 degrees centigrade, all right, times 34 degrees minus 10 degrees. So it's heating up, okay? So our length change would be 0.0115 meters. So that would be 1.15 centimeters. So the rail would expand 0.575 centimeters on each side. So if they both expand, the gap should be 1.15 centimeters, right? Now, on train tracks, they weld them, all right? If you ever walk down a train track for miles, they'll all be welded together. And the reason for that is they don't want them to come apart. But every now and again, you'll find an area which will allow for expansion contraction, and there's basically something that fits over the top of it, and it contracts and expands underneath it. All right. If we use shorter pieces of track and lay them a little farther apart, the gap would be okay for the track when it is cold and when it gets hot. Okay, so we did the exact same thing we did before. Instead of using 40 meters, we use 10 meters. And you can see that the expansion is much, much less. Okay, so now when you think of train tracks, and they might go for a mile, and they're welded all the way down for a mile, that expansion is going to just get bigger and bigger and bigger. So they have to then put in an expansion joint area where it allows it to move back and forth. Okay. Volumetric expansion. Now that has to do with volume, just not linear. Delta V is the change in volume. VO, that's original volume. Beta is the volumetric expansion constant, which is also in the chapter. And then, of course, change in temperature, same thing, all right? So a car's 22-gallon gas tank is filled at 15 degrees Celsius. After it's been sitting in the sun, the temperature rises to 32 degrees Celsius. How much gas spills out of the car? Now, have you ever noticed when you open up the little door where your gas cap is, there's a warning. It says, do not fill it up basically up the neck. All right. When it clicks, then you're done. All right. A couple cents here, one way or another is fine, but don't put another dollar in. All right. And the reason for it is because gas is kept underground, where the normal temperature is about 15 degrees Celsius underground. All right. So when it goes in your car, it's colder. All right. When it gets in your car and it's a nice warm day, it heats up and expands and will actually spill out of the car. So, volumetric expansion formula. The 950 times 10 to the minus 6 is our beta, which is our volumetric expansion. Our initial volume is 22 gallons at 17 degrees Celsius. So that change in temperature is going up 17. All right, so the two temperatures subtracted from each other. So this is a little over a third of a gallon. That is a lot of gas. If you filled it up the neck, it would all come out. All right. It says now if the metal tank expands due to the same temperature change, how would that loss be affected? Well, if you think about this, if you have a gas tank, it's made of metal, all right? And this is the volumetric expansion for metal for what the gas tank's made out of. All right, if the gas tank increases 17 degrees, its volume will increase by 0.013 gallons. So it will allow for just a little bit less gas lost, okay? All right. Okay, so this chapter, there's basically two formulas that you're going to use, all right? Linear expansion, volumetric expansion. It's a super easy chapter, okay? And all of this stuff kind of comes into play where in industry, there are different types of things that go on. And one of them is like a lot of times what they'll do is like if you wanted to put something into something and not have it come out, all right? Like let's say you have a donut and then you're going to stick a rod in the donut, okay? If you heat the donut up, all right, it starts out like this, it expands outward, okay? Or in volumetric and linear expansion, when you heat it up, it expands outward, okay? And then if you put in the rod, as it cools, it will then clamp down on the rod and it will not come out. I mean, so they do stuff like that in industry all the time. It works really, really well. Another thing is, if you think about, remember the, let's see if you can see this here. Remember the thermostats that are the circle, right? And it has a little arrow. And you turn it to heat up or cool down your house, all right? What that is, that's a bimetallic strip, okay? And on that, I'll show you. Basically, if you take this off, this is what you'll see. You'll see a coil and in this coil, there's two types of metal, okay? I think one is either copper or brass, and I think like nickel or aluminum. I've just a bunch of different ones on there. And each one has a different linear expansion, okay? So what happens is when you put your thermostat on, all right, there is a little contact right here, okay? When the house heats up, the metal expands and it spreads itself apart and it moves apart. So this will all of a sudden make contact over here. And what this is either the on button for air conditioning or it's the off button for heat. When the house cools, all right, now it starts to contract and it will turn this way. So now when this side hits over here, that would be the off button for air conditioning, or it would be the on button for the heat to kick out in your house. And this distance here between the two is usually somewhere between 2 to 3 degrees. So if you set your thermostat at 70, your temperature in your house is going to be somewhere between 67 to 72, somewhere in that range, depending on the type of thermostat. Digital ones just do it. All right, you don't have to worry about that. But the old ones, you see these in a lot of older houses, the dial ones. That's how they worked. It was a thermostat. Now, where else do you have thermostats? In your car. All right, in the radiator, there's a thermostat. It looks like a little hamburger. And when the temperature of the antifreeze reaches a certain temperature, it pops the hamburger up and allows for the antifreeze to cycle through the engine and through the cooling and through the radiator. When it's not warm enough, it compresses back down, and the only part that's running through is just through the engine. It doesn't go through the radiator. All right. That's why, like every 4 or 5 years, you're supposed to get all of your radiator fluid washed out and put all new stuff in there, because when that gets clogged, that thermostat gets clogged, you can overheat your car. All right. There's a lot of good practical uses for this chapter. It's very easy math. Just make sure you pay attention to your units. Okay. Thanks.